Euler's partition proof is a proof that if you take a number like 6 and you write it as the sum of unique integers, positive integers, you can actually use just 6 on its own. You're not allowed to use any repeats though, and there are 4 ways of doing it. However, if you're only allowed to use odd numbers, well, that would be the only number of ways you could do it if you couldn't do repeats. But if you're permitted to have repeats, you get a couple more. And in this case, at least, it turns out to be the same number of ways. Euler proves that no matter what number it is you're trying to break up, the number of ways of breaking it up as a sum of unique integers will be the same number of ways as odd integers, but repeats permitted. And he does it in a very clever way using polynomials. So let's start by reviewing FOIL. When you do FOIL, you get x squared, that's the firsts of each parentheses. The O, the outers, are x times 3. The inners are 2 times x. And the lasts are 2 times 3. We end up with 4 terms before we combine like terms. What each of these 4 terms has in common is that each one was gotten by picking something from the first set of parentheses and something from the second parentheses. And every sort of combination of something from the first parentheses and something from the second parentheses occurs. If I use the x with 3, or the 2 with this x, or the 2 with the 3, those are the 4 things that can happen. So this can be generalized a couple of ways. If I have like x plus 2 times x plus 3 times x plus 4, let's say, there are 2 things in each parentheses, which makes a total of 2 for each, which is 8 terms before we start combining like terms. So let's look at what these terms look like. So for instance, if I take the x, and the 4, I'll get 4x squared. If I want to get some more x squareds, I can choose to use the 2 with this x, with that x. And I can get one more x squared by using the x, the 3, and the x. And when I put these all together, I get 9x squared. So it's possible to get individual terms. If I only care about what's the 9x squared term of this answer, I can look to see how is it that I can choose one thing from each parentheses and still get x squared, and the answer is by choosing 2 x's and 1 non-x. Well, Euler uses this idea, and he creates an interesting polynomial product and it's infinite, which means its product is infinite also. But we do know some things about the product of this thing. For instance, there's going to be a 1 in it, because that's what I would get if I multiply the 1 times the 1 times the 1, use the 1 from each parentheses, I get a 1 there. I'm also going to have plus 1x, and that's because if I use the x here from this and the 1 from all the others from then on, I would get 1x, and there's no other 1. It's also going to be 1x squared, which I would get by using this 1 with the x squared, with the 1 from then on. different color. But there are going to be two x cubes. And the reason why that is because one way to get x cubed is to use the x cubed with 1s. Or I could use the x with the x squared and 1s. There's going to be two ways to do that. If I wrote those terms out separately, one of them would be 1x cubed. The other one would be 1x times x squared, which is x to the 1 plus 2. And further on down the road, there's going to be an x to the 6th term. And the way I'm going to get the x to the 6th term is, well, I could use x, x squared, x cubed, and then 1s from then on. So I'll come over here and say I could say x times x squared times x to the 3rd, which is x to the 1 plus 2 plus 3, which is x to the 6th. But another way that I can get x to the 6th is by using the 1 with the x squared, with the 1 with the x to the 4th, with 1s from then on. That one I'll write as x squared times x to the 4th equals x to the 2 plus 4 is another x to the 6th. Another x to the 6th is going to come from using this x with the 1, with the 1, with the 1, and eventually an x to the 5th will be out here. And finally, if I use 1s, 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 but somewhere down the road there's an x to the 6th, and I use that x to the 6th and use 1s from then on, I get x to the 6th. And this becomes 4x to the 6th, but notice that it's 4 because there are 4 ways to write 6 as a sum of unique integers. And this polynomial up here is a polynomial whose coefficients would be, the coefficient of the x to the 6th would be the number of ways of writing 6 as a sum of unique integers. The coefficient of x to the 10th would be the number of ways of writing 10 as the sum of unique integers, and so on. So we're going to bring this guy back later. Euler creates a second polynomial. And this one is pretty involved. So we have here, each of these parentheses has 1, and then x to some odd power, x to the 1st, x to the 3rd, x to the 5th. And then the third term of each one is, oops, this needs to be just 1 plus 1, not. So the third term is x to the 1 plus 1 in this one. The next one is going to be x to the 1 plus 1, and so on. This second parentheses here is 1 plus x cubed plus x to the 3 plus 3, x to the 3 plus 3 plus 3. Now, if I want to jump to see what the x to the 6th coefficient is going to be, I think, how can I get x to the 6th? Well, one way is to use this one with this x to the 3 plus 3 with this one. And if I do that, I have x to the 3 plus 3 equals x to the 6th. But another way to do it would be to use this x to the 1st with this 1 with this x to the 5th. And I get x to the 1 plus 5. And another way would be to use x to the 1 plus 1 plus 1 and x to the 3 and 1s from then on. To get x to the 1 plus 1 plus 1 plus 3. And a final way would be somewhere down the road there's an x to the 1 plus 1 plus 1 plus 1 plus 1 plus 1, and use that with 1s from then on. As you can see, there are 4 of these, and the coefficient would be 4 to the 6. Notice that this 4 is the number of ways of writing 6 as a sum of odd numbers with repeats permitted. So this polynomial up here is the special polynomial whose coefficients, when multiplied out, would be the ways of writing the exponent of each term after combining and all, so that it's the sum of odd numbers with repeats allowed. So the final part of this proof is for Euler to show that this polynomial, this guy, this gigantic product, is equivalent to this other gigantic product. And if they're equal, see, when two polynomials are equal, I'm just going to say like ax squared plus bx plus c is equal to dx squared plus ex plus f. If a, b, and c are numbers 1, 2, and 3, for the polynomials to be equal, d, e, and f would also have to be 1, 2, and 3. So if I multiply out that giant first polynomial, the 1 plus x times 1 plus x squared going on thing, that's going to have 4x to the 6. There's 4 ways to write 6 as a sum of unique integers, whereas the other guy, 1 plus x to the first plus x to the 1 plus 1, 1 plus x to the third, all those, that's also going to have 4x to the 6. But that 4 is because there are 4 ways to write 6 as a sum of odd numbers with repeats allowed. So if these two polynomials are actually equal to each other, not just will these coefficients be equal, 4 and the 4, but all coefficients will be equal. Well, here's the way he does it. First, a little refresher. You might remember that if you add 1 plus a half plus a quarter plus an eighth, this is a geometric series. And there's a formula for the sum of the geometric series, which is a over 1 minus r, where a is the first term, and r is the common ratio, which in this case is actually 1/2. And the sum would be 2. Now, this formula can also be worked in reverse. If I have something like 3 over 1 minus 2/3, I could change that back into a geometric series. This is a, this is r. So it's a, then a times r squared, going on. So you can go back and forth. If you ever see something that's something over 1 minus something, you could turn it into an infinite geometric series. So let's see how this relates to the problem. The second polynomial, the 1 plus x to the first plus x to the 1 plus 1 plus x to the 1 plus 1 plus 1 going on, 1 plus x to the third plus x to the 3 plus 3 going on, odd numbers all the way down. Each of these individually is can be turned into a geometric series, or it is a geometric series, where a is 1 and r in this case is x to the first. So this whole thing could become 1 over 1 minus x. Likewise, this is also a geometric series because you multiply 1 times x to the cubed, x cubed, you get x cubed. You multiply x cubed times x cubed, you get x to the 6, which can be written as x to the 3 plus 3. So this thing is also, and the next one would be 1 minus x to the 5th. So now this gigantic thing has been turned into this still infinite but smaller looking thing. Now, what can we say about this smaller looking thing? Well, here's what it looks like now. 1 over 1 minus x, 1 over 1 minus x squared, x to the third, 1 over 1 minus x to the 5th, going on forever. Euler says we can multiply top and bottom of this as long as we multiply by the same thing. And his thing that he's choosing to multiply by is 1 minus x squared times 1 minus x to the 4th times 1 minus x to the 6th going on for both of them. So basically this is 1. We're multiplying top and bottom by 1, so we're not changing the sort of value of this thing on the left. Well, each of these things is a difference of perfect squares. Any x with an even exponent itself is a perfect square. So the 1 minus x can be replaced with 1 minus x squared can be replaced with 1 minus x, 1 plus x. And the 1 minus x to the 4th can be factored into 1 minus x squared times 1 plus x squared. And the 1 minus x to the 6th can be factored into 1 minus x to the 3rd, 1 plus x to the 3rd. These bottoms I'm not going to factor. But now I'm going to do some canceling, like this 1 minus x can be canceled out with that. And the 1 minus x squared can be canceled out with this. And the 1 minus x to the 3rd can be canceled out with this. And the 1 minus x to the 4th, that's eventually going to happen next, we can cancel that with this. And the 1 minus x to the 5th will get canceled out with this. And the 1 minus x to the 6th will get canceled with this. And there's not much left that remains, just this, this, this. 1 plus x, 1 plus x squared, 1 plus x to the 3rd, dot, dot, dot. Well, this thing is actually equal to this guy. So what that shows is that this polynomial up here is equal to this polynomial up here, but this polynomial's coefficients after you multiply it out is the ways of writing the exponents as the sum of unique integers, whereas this one, when we multiply it out, it's the way of writing the exponents as the sum of odds with repeats allowed. So if the two polynomials are equal, that will also imply each coefficient is equal, and if each coefficient is equal, that means it was not an accident that there were 4 ways to write 6 as a sum of, it's not a coincidence that there were 4 ways to write 6 as a sum of unique integers, and also a number of ways to write 6 as the sum of odds with repeats permitted. So you might wonder, aside from asking you to reproduce this proof, what kinds of test questions could we ask? Well, I could do something like this: 1 plus x, 1 plus x to the 3rd, 1 plus x to the 7th, 1 plus x to the 8th. I ask a question like, what's the x to the 10th term? Let me stick in also 1 plus x to the 9th. So you'd look at this and say, well, I'm looking for numbers that add up to 10 between 1, 3, 7, 8, and 9. So 3 plus 7 adds up to 10, 9 plus 1, those seem to be the only 2 ways, so it's 2. But I could do something like that. As far as the other guy goes, 1 plus x to the 1st, 1 plus x to the 1 plus 1, plus x to the 1 plus 1 plus 1, dot, dot, dot. And now I'll also throw in x to the 5th, x to the 5 plus 5, dot, dot, dot. And this thing won't be infinite. And I'll say, what's the x to the 10th term of that? Well, when I look at this, I could get x to the 10th with this guy, or with this guy together with some x to the 1 plus 1 plus 1 plus 1 plus 1. Or I could use all 10 ones. Basically, it's the ways of writing 10 as the sum of 1s and 5s. 5 plus 5, 5 plus 1 plus 1 plus 1, or 1 plus 1 plus 1 plus 1, 3 ways. I could even, if I want to be sort of extra sneaky with that other question, I could write the same question this way. this is and say what's the x to the 10th coefficient. Well, you'd have to look at this and imagine that this got expanded and this guy got expanded, and it becomes the same question. It's the number of ways of writing 10 as the sum of just 1s and 5s with repeats permitted. 5 plus 5, 5 plus a bunch of 1s, and 1 plus a bunch of 1s. So those are some stuff.